In this section, we will talk about function. And before I start this section, let me go back to our unit 2 example from unit 2. So here, in this example, in 2010, there were 1400 Canada Geese. In 2016, their population increased to 1820, and we write an equation for the population of Canada Geese y. So our y is the population in terms of x. Our x is the number of years since 2010. So here we have this equation. In this equation, y equals to 70x plus 1400. So this is an equation. This is an example from unit 2. Okay, let's see. Now this equation, it gives us the number of geese population. Okay, and our x is the number of years since 2010. Now on what variable our value of y depends in this case? So the value of y, it depends on x, right? So if our x is 0, what will be the value of y? 1400. If the value of x is 1, it will be 1470, right? So the value of y depend on x. Now, we can also tell this that our y is related to x. We have our y in terms of x, or the other way to tell this is our y is a function of x, and we will talk in detail. Okay, so here our value of y, it depends on the value of x. Now if we take a unique value of x, do we get unique value for y? Like for example, if we take a different value of x, do we get different value of y? Or is there any value of x, two different value of x, which give us same value of y? So no matter what value of x you take in this equation, we always get a different value of y. Do you agree? Like if x is 0, we get 1400. If x is 1, we get 1470. If our x is 2, we get 1540. So for different value of x, we get different value of y. Okay. Now, and this is a function. This is one example. So we also had our linear equation in terms of y. So you have seen that we write our linear equation y equals to, just let me take 2x plus 3. So here this is our linear equation. We have our y, okay, and we rewrite y in terms of x. Our value of y, it depends on value of x. Now let's go back to our unit 3 here. Now before defining the function, now let's talk about the relation. So let's take any two set. So let's take any two set. Okay, so this is our set A and this is our set B. If we are talking about set, what does set contain? It contains element, right? Or we can have an empty set, but let's take these two, A and B are not empty set. It means they do have some element. So let's take set A has elements like 1, okay, -2, 0. So 1, -2, 0 are the element of set A, and we have a set B, and set B has an element like A, B, C. So we have a two non-empty sets. Okay, set A, set B. Each set has some elements. Set A has an element 1, -2, 0, and set B has a element A, B, C. Okay. Now for each element of set A, if we can find at least one element from set B. So let's take our 1 is connected to, so let's consider 1 from set A is connected to B, or 1 has a relation with A. Similarly, negative 2 has relation with C, 0 with B, 0 with C, or just say this is just an example, okay? Now here we have a 2 set, non-empty set. A has element 1, negative 2, 0. Now in this example, every element from set A, so we have 1, we have negative 2, we have 0. Every element from set A has at least one element in set B. Do you see that? Like for example 1, how many elements it has on set B? 1 element, right? So 1 has element A. What about negative 2? Negative 2 has how many elements on set B? We have A and C. We have 2 elements. In a similar way, 0 from set A has 2 elements on set B. So in general, every element from set A has exactly one element in set B. Okay, and if we see this kind of correspondence or connection, we call that A has a relation with set B. Okay, so set A has a relation with set B. So to be in relation, every element from first set has to correspond with at least one element from second set. Now let me take example here, another example. So we have a set X. X has a negative 5 to 3, and we have a set Y, and Y has a 4, 10. Okay, now let's see. So this is what is given to us. Now is this a relation? Can we tell that X, there is a relation between set X and Y, if this is the case? Now what is missing here? Now yes, 2 does not have any connection with element from set Y. Okay, so to be in relation, every element from first set. Okay, so our X is the first set. X has the element negative 5, 2, 3, and every element from X must have at least one element in set Y. You can have more than one, it does not matter, okay, to be in relation. But every element from set X must have at least one element from set Y, okay, to be a relation. But in our case 2, it does not have any element in set Y, and because of this, this is not a relation. Okay, so there is no relation between set X and Y. So let me take different case here. So for example, let's say we have a, so this is our set A, and this is our set B, 1, 0, negative 1. So 1, so A has relation with every element from set B. Now is there a relation between set A and set B in this case? Yes. Okay, we have only one element in set A, okay, and that element has a connection with 3 elements. Okay, it has to have at least one connection, but it's okay if it has more than one connection. Okay, so in this case, we have a relation between set A and set B, so there is no relation between set X and Y, so there is relation between set A and B. Okay, now let me take one more case. So we have a set X, we have a set Y, so we have, let's take P, Q, R, and we have, okay, A, B, C, D. Now, so what about this? Is this mapping is a relation? Do we have a relation between set X and Y? Okay, yes, that's true. Okay, so to be in relation, every element from first set, so we have P, Q, R. If they have at least one element in second set. So here P has one element A, Q has one element B, R has one element D in Y. Okay, now this is a relation. So there is a relation between set X and Y. It doesn't matter if C has any element in set X or not. Okay, you have to check whether every element from first set has correspondence with at least one element in second set or not. Okay, so if every element from first set has a correspondence with at least one element from second set, we call it a relation. Okay, so here set X and Y has a relation with set Y. Okay, now once we have an idea of relation, we'll define the function here. So to be a function, okay, so to be a function between set A and set B, every element from set A, there if we can find exactly one corresponding element in set B, then we call it a function. So to be a function, every element from first set must correspond exactly one element from second set. Okay, let's find the difference here. Okay, so to be a relation, if every element from first set correspond at least one element from second set, it's a relation. But to be a function, every element from first set must correspond exactly one element from second set. Okay, there's a keyword, so exactly one element. So if every element from first set correspond exactly one element with, then it's a function. If every element from set A correspond at least with one element, then it's a relation. Now let's go back to these examples. Now what about this first mapping? Is this a function? We know this is a relation, right? Every element has at least one element in set B. So this is a relation. But what about function? Is this first mapping a function? No. Why this is not a function?
Because -2 and 0 both relate to 2.
That's right. So -2 and 0, it has more than one element. Okay, it corresponds with more than one elements in set B. So -2 corresponds with A and C. 0 corresponds with B and C. To be a function, every element must correspond with exactly one element in set B. Okay, so this is not a function. Now what about this one? Second mapping. Is it a function? Now this is not a relation, right? So this is not a function, and because 2, it does not have one element from set Y, and -5 has 2 element from set Y. Okay, so this is not a function. What about this third mapping? Is this a function? This is a relation, but is this a function? To be a function, every element from first set must correspond with exactly one element from second set. In our first set, we have A. This A corresponds with 3 different elements, and because of this, this is not a function. Now what about our last mapping? Is this a function? Okay, now our last mapping, this is a function because every element from set X, so we have a element P, we have element Q, we have element R. Okay, every element from set X corresponds exactly one element. So P has exactly one element, Q has exactly one element, R has exactly one element. Okay, so this mapping is a function. Now let me take more example. So let's say we have 10, 9, 8, and we have 4. Now, is this a function or not? Is it function or not? To be a function, every element from first set must correspond exactly one element from second set. Is it function or not? Yes. Okay, it does not matter if they correspond with same element. Okay, so here we have a 3 element, and you have to check whether those three element has exactly one element from set B or not. So 10 correspond to one element 4, 9 correspond to one element 4, so 8 corresponds to one element 4, and this is a function. Okay, so this is a function. Okay, so let me take, okay, what can be the another case here? Okay, so we have, okay, I think yeah, this should be the enough example here. Now, once we have a function, so this is our function, okay, from set A to set B. This is also a function, okay, from set X to set Y. Now, we call for element from first set as a input or a domain, okay. So every element from set A, we call it input or domain. Okay, so element from first set is input or domain in a mapping diagram, and element from second set we call it output or range. So this is the case when we have a mapping diagram. Okay, now let me take a different example here. For example, we have a set here. Okay, so we have -2, 1, 1, 5, 1, 2, 6, 1. So we have this a set of order pair. Okay, now, so here in every order pair, our first element is X, second element is Y. Okay, now we can draw this set of order pair in a mapping diagram. So this is our X, this is our Y. So you write down first element in the first set. Okay, so do not repeat. So we have -2, we have 1 here, 1 here. So let's write down 1, and we have 6 here. And the second element is Y, and let's collect all those second element in our set Y. So we have 1, 5, 2. Now, so we have -2 and 1 together. It means -2 it has correspondence with 1. So -2 has correspondence with 1. 1 is connected with 5. 1 has connection with 2. 6 has connection with 1. Now, is this mapping a function? This is not a function. And why this is not a function? Because 1 has a correspondence with more than one element. Okay, so this is not a function. Okay, but it's still every element from our first set, these are the input, and every element from the second set, these are the output. Okay, now in general, so these are the very specific example. So in general, so we represent our input or our domain by X. Okay, so in general, we represent our domain or our input by X. Okay, and we have our output or our range, and we use Y to represent our output or our range. Okay, so on our Cartesian coordinate system, we have a horizontal line x-axis, and every point on the x-axis, they are the input, we take them as the input, and every point on the y-axis, we take them as a output or a range. Okay, so this is the general representation. And if we have a function between these two sets, so let's say they have a function here, so this f represents that we have a function between set X and set Y. Okay, now our output Y, so we have output Y, and we can rewrite our Y as a function applied to this X. So we have a function, okay, of X, f of X. Okay, now here you can you can think of okay, just let's take an example. Okay, for example, so we have ingredients for pizza, okay, and here we have a pizza machine. Now once you have the ingredients, so these are the like raw materials for pizza, okay, and this is our pizza machine, okay, so this is the machine here. Now when you have everything ingredients for pizza ready, what do? You put your pizza in the pizza machine, and what do you get at the end? You get the pizza ready to eat, right? So here, this is your input, okay, so we use the ingredients of a pizza as an input or a domain, okay, and our pizza machine, this is a function, okay, so this is the function here, okay, and when you use this function, when you use the pizza machine to these ingredients, we end up getting the pizza ready to eat, and this is our output, okay. This is the output, this is the input. Now here, now let's go back to this y equals to f of x. Y is output or a range, okay, every time now onwards. If you see y, it is always output or a range. If you see x, it is always domain or a input, okay. So do not get confused. X always represents domain or a input, y always represent output or a range, and we can rewrite our output y as a function, okay. This is a function. F is a name of a function. It can be a linear, it can be a quadratic, it can be cubic, okay, it can be any function, okay. We have this function and we apply this function to our input x, okay. So you have a function, you apply your function to the input, and we get a output here. Now how do we read this? So this is, we read this as a f of x, okay. To read this is f of x, or function f at value at x, okay, or we can also call the value of function f when input is x, okay. But this is not, okay, so this is not f times x, okay. So you see that, so we have f parenthesis x, okay. So this is not f times x. There is no, so there is no product sign here, okay. So there is no product sign. So this is a notation for the output, okay. So you have these three options to read this expression. Do not read this as a f times x, okay. This is the f of x, or the function of f at x, or the value of function f when our input is x, okay. So keep in mind, so this f of x is not f times x, okay. So we are not multiplying f and x here. We are finding our output when our input is x, okay, and your input is always inside the parentheses, okay. So our f is of name of a function, okay. If you have a function and if you have a parenthesis, and whatever we have inside this parenthesis is always our input, okay, and our y, it always represents the output. Okay, any question on this notation here? So in general, so to be a relation, every element from first set must correspond with at least one element from second set. That's the relation. To be a function, every element from first set must correspond exactly one element from second set. That is a function, okay. Now first element or the collection of every element from first set, we call it input or a domain. Okay, collection of element from second set, we call it a range or a domain. In general, our X always represents domain or a input. Okay, Y represent output or a range, and we can always rewrite our output Y as a f of x, function applied to our input x. Okay, so these are the basic thing you have to know. Okay, any question up to here? Now let's go and see what examples here we have. Okay, now we have example here. Which of the following correspondence satisfy the definition of a function? Now the input value is one of the letters from J, F, M, A, S, O, and D. Okay, so our inputs are J, F, M, A, S, O, and D. So these are the inputs. Okay, so these are the inputs, and the output value is a name of a month beginning with this letter. Now let's make a mapping diagram. So we have a first set, and first set is always our input. And what do we have as an input? We have these letters as an input. So we have J, we have F, we have M, we have A, we have S, we have O, N, okay, and D. So this is our input. Okay, now what is the output value? Output value is the name of a month beginning with these letters. Okay, now let's make a collection of output here. So what name of a month do we have starting with J? June, July, right? So we have June, July. Okay, with F we have February, right? So with M we have March, we have May. With A we have August. With S we have September. With O we have October. With N we have November. With D we have December. Now let's see. So here J has a June and July, F has a Feb, M has a March, May, A has August, S has September, O has October, N has November, D has December. Now, is this correspondence of function? That's the question here. Is this a function? To be a function, every element from first set must correspond exactly one element from second set. Now, is this a function or not?
Are we grouping March and May as one element?
No, they are separate. Okay, so if you want, okay, you can just. So let me rewrite this. So we are not grouping. Okay, so just let. Okay, so let me write July here and May here. Okay, J has a July, M has a May. Okay, now is this a function or not? No, because J and M, it has more than one element from set B. Okay, other than J, except J and M, every element they has exactly one element from set B. But J and M, it has more than one, and because of this, this is not a function. Now in this, but now is this a relation or not? It's a relation, right? Because every element has exactly one element from set B. Now, so what is the input or a domain for this case? So what are input or a domain? Every element from first set. So J, F, M, A, S, O, and D. All these elements are an input or a domain, and all these name of a month are a output. Okay. So this is not a function. So not a function. Okay. So A is not function. Okay. Okay, we don't have a table here, so let's skip B. Now let's go to number C. The input value is the radius of a circle and the output value is the area of a circle. So our input is a radius of a circle. Let me just write down R, and our output is area A. Now, will this be a function or not? So you have a radius, and what numbers you can pick for radius? So what can we have as for a radius? Radius can be any number greater than 0, right? So you can pick infinite number as a radius. Now for each radius, do we get exactly one area or more than one area for a circle? So okay, now to find the area of a circle is a pi r square, okay, and pi is 22/7, right? So this is the area. So we have like infinite value for r. So you can take r any number greater than 0, okay? Now for each value of r, do we get exactly one area or more than one area? Like for example, you take circle of radius 5. Now how many area of that circle do you get? Do you get one area or more than one? One, right? So for every r, we get exactly one area. So it means this is a function, okay? So in general, just let me use this. So here, for each value of r, we get exactly one area, okay? We can't get, okay, yeah, for two different radius. So if we have a circle with a two different radius, means those two circles has a different area, okay? So this is a function. Okay, now, so if our input is a name of a student of this class and our output is a height, will that be a function or not? Our input is every one of you. Name of, so we have, so this class has like a 30 students. So our input is our input set has all those 30 names. Output is a height of each student. Now, will that be a function or not?
Yes.
Why not? Now to be a function, so our first set is element. First set is you, okay? And for each of you, we measure height. Now, the question is, does every one of you have some height? You all have some height, right? Now, can one person have more than one height if we measure now? Is it possible to have more than one height? So every one of you has exactly one height, right? Some of you might have same height, it doesn't matter. Okay, so here, so we have our input, and our inputs are like name of you. Let me call ABC, okay? And each of you has a height, okay, let's say 5, 6, 2, okay, 5, 8. Now A has a height 5, 5, B has 6, 6, C has a 5, 8. Okay, each of you has exactly one height. And does that make a function or not? It's a function. Okay, so let's do this once for